Well, thank you very much. So you're all graduate students? And what fields? Chemical?
Chemical.
Mechanical? How many mechanicals? I'm a mechanical. I advise materials students as well as chemical engineering and mechanical and aerospace engineering students. So thank you for the very nice introduction. I'd like to kind of give you kind of a view of our facilities and where we work. This is Zucro Labs. This is an office building. And then we have several different laboratories. This propulsion lab is one of the oldest. That's where we do a lot of our work. And this is our newest facility. It's dedicated last year. And in fact, this is another view of that. The thing about that that's very unique is the full length. It's like 100 feet. I guess I have to convert that to meters. Huh? So 30 meters long and about 20 feet wide in this area. And that is a big laser lab. But the thing that makes it unique is it's connected to these large test cells. And in most of the test cells, we test jet engine, combustion types of systems, turbulent combustion, and these three. And this one on the end, turbine blades. So there's a lot of air-breathing propulsion, rocket propulsion. Most of the rocket propulsion is back over here. And in this test cell, we do some energetic materials. And I'll kind of define what energetic materials are in a minute. Here's some of our other facilities. This is a new lab. It's a multidisciplinary lab. We call it the Flex Lab, so it's flexible for different parts of different engineering departments have space. And our Energetics Research Center has a lab space here. This is one of our new faculty that synthesizes energetic materials. So it makes new molecules, new propellants and explosives and so forth. And that's where his main lab is now. And this is Herrick Lab. Has a lot of industrial connections, a lot of heating, cooling. The whole building actually is a laboratory for heating, cooling types of things. And we do some inkjet printing of nanoscale thermites. Anybody know what a thermite is? I know John does. Okay, so this must be your group over here, John, right? So it's like metal oxides. And so we're printing some other energetic materials as well. And I'm going to talk more about some other additive manufacturing that we do as well. But we do that at that building. Here's a couple other facilities that our Energetic Research Center uses. And this is our engineering college headquarters, as well as aerospace and materials engineering. And in the basement of that, there's gas guns, so high rate mechanics. So you shoot projectiles fast into things and break things and study that. Professor Wayne Chen is our key person for that. This is Boeing Lab, where he has mostly what goes on in there is civil engineering. You have buildings, and they have big earthquake simulators. But he has labs in the underbelly of it with big, long. Does anybody know what Kolsky bars are? Hopkinson bars. It's basically high rate mechanics of looking at including energetic materials. So, what are energetic materials? They're combustible materials that you don't need any extra oxidizer. So they carry their oxidizer, with them. That's in contrast to like gasoline and hydrocarbon fuels, where you're normally burning with the oxygen in the air. Like most combustion systems, it's very temperature sensitive in terms of the reaction rate. So they could be stably stored for a long time, and then when you need to ignite them, then you apply ignition source to that. Think of your airbags in your car. They're there. They're hopefully going to be ready to go when you need them, and you apply an ignition, and then they can react very quickly, produce a lot of gas in that case. A lot of times energetic materials produce a lot of heat as well. And it's easy to, one way to differentiate energetic materials is by their applications. There's energetic materials used for explosives, and not just for military, but also for road construction, building construction, so forth. Propellants, and that could be gun, rocket types of propulsion, and pyrotechnics. Somebody said they wanted to come to the seminar because it was fireworks. So pyrotechnics fit into that area, but there's also military applications for pyrotechnics, countermeasures, flares, those kinds of things. delay charges. So since not all of you are combustion scientists, I thought I'd define combustion a little bit. Combustion includes both deflagration and detonation. So you might say, well, wait a minute. It's like, I thought combustion means just burning. No, I mean, you can burn in different ways. A deflagration is commonly what you would call combustion or burning. And it's a reactive wave. It burns through a material propagated by diffusional processes. So heat conduction, mass diffusion, and that's what's throwing the energy forward and heating fresh material up to an ignition point, and then that reacted material is driving the energy that's propagating that wave. So this is an explosive material, and it's just deflagrating. This is the same, oh, let's see, I'll show that again, didn't repeat. This is the same material, goes up, hits a detonator, and that detonates. And you probably think, well, detonation, explosion, isn't that the same thing? All detonations are explosions, but not every explosion is a detonation. A detonation is also a reactive wave. It's a subset of combustion where it involves a shock wave, and then behind that you have reactions, and the reactions provide the energy to sustain that shock wave. Usually if you put a shock wave into something, you hit it hard or push on it with hard with a piston or something like that, that shock wave will dissipate with time. If you have a shock wave with reaction behind it and that material that can detonate, that reaction will sustain itself and it will sustain that shock as long as you have that explosive material. So how's the energy transported? There's some chemies in here, so transport phenomena is a familiar term to you. How is that energy transported forward in a detonation? Well, it's actually by acoustics. So the reaction behind the shock wave produces energy and pressure, and that energy is transported up forward acoustically, and basically it piles up into that shock wave and sustains that shock wave. So it's a very interesting phenomena. Usually when you think of an explosion, it's like, oh, all this chaos, and there's nothing really ordered or that you can understand in detail, but it's a very precise thing. So I'm going to talk a lot about solid propellants. So I want to kind of explain what typical solid propellants are. So if you think of a solid propellant, a composite propellant, it has 2 or 3 components. One component is a rubbery binder that holds it all together. The rest of it are particles. Some of those particles are oxygen rich. We call those oxidizers. You can think of those powders looking a lot like salt or table sugar, but you don't eat it. It actually will take your thyroid out generally. It's like ammonium perchlorate, so it has a lot of oxygen. And the binder not only holds things together, but it's multifunctional. It's the fuel. And often, and this is a shuttle, and this is a solid rocket motor. And this is a schematic of these. This would be the oxidizer. We also put aluminum powder into propellants. For example, with the shuttle rocket motors. So why do we put aluminum into a solid propellant? Any ideas? It's a sensitizer. A sensitizer? Nope.
Does that increase the reaction rate?
Nope. It does a little bit, but that's not the main reason.
It can pull the oxygen off the iron.
If you put iron in there, iron oxide. Iron oxide is a catalyst that you sometimes put in propellants as well. Aluminum is another fuel, and it raises the temperature a lot. Okay, so if there's no aerospace engineers here, right? We don't have aerospace engineering. But if there were, they would tell you if you want to improve the performance of a rocket, you want to raise the temperature, and you want to lower the molecular weight. Well, aluminum doesn't help you with the molecular weight, but it does raise the temperature a lot, and so that improves the combustion efficiency and what they call, they look at as specific impulse. So we'll talk about actually putting other metals in. So I'm basically a combustion guy. I like to burn things, and my world is either oxidizers or fuel. So everything could be part of a combustion system. So when I see aluminum, when I think about aluminum, I go, well, that's a fuel. If I look at other things, like fluoropolymers, for example, That's an oxidizer. It has fluorine. So that, so you could take aluminum. So your frying pan has a Teflon and aluminum. You guys are mostly interested in nano-energetic or nanotechnology, right? Well, if you take, nanoscale Teflon particles, nanoscale aluminum particles, mix those together, and you've got an energetic material. And it's right there in your frying pan. So this is a strand of propellant burning. So this, one thing we like to do is be able to tailor the performance. And some recent things we've done is, and I mentioned iron oxide as a catalyst. We've encapsulated catalysts in ammonium perchlorate, which I said is a typical oxidizer in propellants. And we do that by a very simple, we're mechanical engineers, so we've got to do simple things with chemistry types of stuff. So we do a solvent, anti-solvent crystallization process. We suspend the catalysts, which are nanoscale iron oxide, and we've used other materials as well. Graphene that has suspended nano catalysts as well. We have that in our solvent. We dissolve the ammonium perchlorate. We add in an anti-solvent, and those nanoparticles act as nucleation sites for the crystal growth. So the crystals grow around the catalyst. So why would you do all that in a solid propellant? You could just throw it into the solid propellant, which is typically done, and the binder could hold it all together. But the oxidizer crystals are the component of the propellant that really needs the catalytic performance and the improvement. In addition, the catalysts that are in contact with these polymeric binders, they're like rubbery materials. In fact, the final solid propellant is like a pencil eraser. It's kind of a rubbery type of material. The catalyst that if you just mix it in, what is traditionally done, into the binder system, it catalyzes the aging of the polymer. So there's some material scientists in here. You know that polymers degrade with time. So your solid propellant can degrade with time as those catalysts accelerate that aging. You don't want that. So it's better to put it inside the crystals. We showed that it's more effective in catalyzing the burning. One other effect is if you think about this composite material, it has to have good mechanical properties, because if it starts to form cracks inside your rocket motor, the flames will go down to the cracks, and that'll open new cracks, and then you have an explosion rather than propulsion. And if you bring in, and catalysts, you want high surface area. That they work better if you have more surface area. So you like the nano size, but if you want to put that into your propellant, you have to sometimes add more binder if it's really high surface area catalyst. And you don't want to do that because you're starved for oxygen already. You're trying to bring in as much ammonium perchlorate as possible. So to bring in a really high surface area catalyst, you have to sacrifice performance. But if you put the catalyst inside the crystals, and you basically, John and I talked about core shell types of materials. That's a kind of core shell material. Put the catalyst inside the crystal. You don't have to have the binder hold that all together. We've also looked at, and I'll talk a little bit about this, looking at micron-sized aluminum particles, which is typically used in propellants. Over the last couple decades, people have looked at nanoscale particles added to propellants. But what we did is micron aluminum particles that have nanoscale features. And I'll talk a little bit more about that in a minute. Alloyed metals. So aluminum is used everywhere in propellants, explosive, and pyrotechnics. We looked at an alloyed material, aluminum lithium, because it has some really interesting properties. We can apply just thermochemistry calculations and show that theoretically we would get better performance. Remember what I said, a specific impulse improves if we have lower molecular weight or higher temperature. The temperature drops a little bit with aluminum lithium versus aluminum, but the molecular weight drops enough that the performance goes up. But just as interestingly, the lithium is halophilic. Now you're all engineers, so you're like, what the heck is halophilic? Anybody know it?
It likes things like halogens.
Yeah, that literally means it loves halogens. Halogens like chlorine, ammonium perchlorate. So it has chlorine in there, so the typical solid propellant produces HCl. What do you think HCl does to your launch site and acid rain, all that stuff? Not a great thing, right? It'd be nice to get rid of that, but people have looked at additives and it kills performance. You're cutting the energy. The lithium, being halophilic, forms lithium chloride instead of lithium oxide, and so it ties up that chlorine and and you produce hydrogen instead without the HCl. So it's less toxic pollutants and less caustic. And then, and I'll talk about this as well, we've done some reactive wires, and I'll explain what that is. It's basically kind of blending pyrotechnics with propellants. And now, and I'll talk some more about this too, we've done some additive manufacturing. I mentioned with inkjet printing, but also fused deposition and viscous printing. So metallic fuels, and like I said, it's perfectly normal for us to think about burning metals, and we do all the time. But let's think about, has anybody heard of emulsion fuels or emissive fuels? If you burn liquids, often you have it. All liquids are a mixture of different hydrocarbon, fuels, and so and often those are emissive. They mix well with each other. Okay, water and alcohol are emissive, right? They mix well. There's also emulsion fuels. So think of it like a fuel oil, and you force like water to, water and oil they don't mix naturally. If you force that to mix, maybe using some surfactants and agitation and so forth, you make an emulsion. So it could be a fuel oil with tiny droplets inside there of water. When that's heated in the combustion system, it could shatter and micro-explode those liquids. Likewise, if you have emissive fuels, but the volatility, the boiling point of the constituents are very different, you can have conditions such that the droplets will micro-explode, sort of self-atomize, and form smaller droplets that could burn faster, more complete combustion, etc. So on metals, an analogy to the emulsion fuels is what we call mechanical activation. If you want to think of it just really crudely, we take a ball mill. You have balls inside of containers that are almost like a crazy carnival ride, and smash the materials. You think, oh, that's going to make it smaller under the right conditions. Yeah, you do mill and make smaller particles. Under the other conditions, you can take two constituents, say a polymer with aluminum, and smash or intertwine these materials together, even down to nanoscale features. You could also build that up from bottom up, which is, I think, all the nanotechnology. You think of those kinds of things, and we do work with collaborators on that kind of thing as well. But you can come up with a particle that if you look close, yeah, there's some metal, say aluminum, and there's some polymer. Could be a fluoropolymer, could be a hydrocarbon intertwined inside that aluminum. And that dramatically changes how that particle ignites. Could ignite much easier. And as it burns and heats up, it can burst apart. The polymer could gasify and disrupt that particle. Alloys are an analogy to emissive liquid fuels. And so we've looked at, in particular, this aluminum lithium. We also looked at other alloys. But this one, the theory, the thermochemistry says, okay, look, this could be good for both cutting the HCl emission as well as performance. So, and I'll show that it also has the properties, because lithium is much more volatile, lower boiling point. It can micro-explode the particles into smaller droplets, and that can, very importantly, improve performance. And this is just a schematic of how we, in a very top-down method, almost like sledgehammer approach to making nano-featured materials. We put aluminum and, in this case, Teflon. And what did I say about fluoropolymers? To me, those are oxidizers. So this is an interesting composite particle in that it has some oxygen, or in this case, fluorine, which is an oxidizer for the aluminum. This is a SEM image of that particle. This is 10 microns. So it's actually micron sized, which has advantages in that it could be a drop-in replacement for just aluminum powders. This is looking at the EDS, the electrodispersive spectroscopy. The green here doesn't show up too well, but it's very well dispersed throughout that particle. So we've got Teflon throughout that particle, and it is a nanoscale inclusion. So if we put that into propellants, this is the baseline aluminized propellant. This is the surface, if you look closely here. You can see these particles. Some of these particles you can see tails. That's alumina smoke coming off from that particle. And this is what we call mechanically activated 70-30. So 70% aluminum, 30% PTFE or Teflon. If you look at the surface, there's a lot more bright spots. It's igniting right at the surface rather than as it regresses down and then ignites. And you also see a lot more streaking. That means there's small particles. So what's happened is these composite particles ignite more readily at the surface, break apart into smaller particles, and that's, like I said, it'll improve the burning rate. Combustion efficiency, especially in small rocket motors. And also there's a loss that occurs, it's called a two-phase flow loss in rocket motors. So as the products of the combustion, so what does aluminum go to? When it's oxidized, it goes to alumina, Al2O3. And in a rocket motor, that's liquid. So you actually have liquid droplets. It's combusted aluminum that clunks its way out through the nozzle. Can also be slag in the rocket motor. Neither of which help your performance. They cut into your performance. An easy way to think about why that's the case is think about a hot alumina droplet going through your nozzle. And to get the best performance, you would like all of that thermal energy from that droplet to be conducted out to the gas. That gas is just not going to expand as well, and you're not going to get the thrust as well if you don't get that energy conducted to the gas. If you have small droplets, that's going to be very fast, and it's going to be close to equilibrium, and you'll have lower two-phase flow losses. And those losses can be as much as 10-15% of your performance. Current solid rocket motors just eat that and say, okay, well, that's the best we can do. It's great. Aluminum brought the temperature up, and we'll just suffer with that loss. This just shows we burn strands and collect the particles. This is the baseline propellant, and you can see the large alumina particles that we collect. For the modified, this mechanically activated material, you can just visibly see, and we've quantified this, of course, and as there's a lot smaller products. Smaller products will result in lower two-phase flow losses and better performance for your rocket. As I mentioned, we also have looked at alloys. There's some of you in materials engineering, right? So you guys love these kinds of plots, right? These phase diagrams. And for the materials engineers in here, we're looking at a 1-to-1 atomic aluminum lithium. That's a lot higher content of lithium than what you normally see in a structural material. Usually for structural aluminum lithium, that's on airplanes we fly on. There's maybe under 5% lithium by weight. In this case, it's 20% by weight. Lithium's lighter than aluminum, but it's 1-to-1 atomic, forms a very nice alloy. You look at the boiling point. The boiling point of lithium is 1300 C and some change. Aluminum, much higher. So we have a disparity in boiling points. And so I'll talk more about why that's important. If we throw this into some propellant strands and burn it, what can you notice differently about this? So the strands right here is maybe a 1/4 inch. This is a high-speed imaging, maybe 1,000 frames per second. Otherwise, it would look like a firework. So those that you wanted to come to see fireworks, you've seen some fireworks with a high-speed camera. A couple things I notice on this is you see particles burning far away from the strand. Here, the biggest thing that stands out is the color. And that's lithium will burn kind of a magenta. To me, it looks pink. And then look at all the dark space. What does that mean? Those particles are pretty much consumed and done before they move very far downstream. And also kind of seems to be kind of exploding in an interesting way. Let's look microscopically. We do some backlit, high-speed microscopic imaging. The smallest particles you see here, those are aluminum particles. Those are about 30 microns to give you a scale. The droplets here are several hundreds of microns, maybe the diameter of your hair. This is all pretty small stuff. But you can see that as this surface burns back, and we're not really seeing the flames because of the backlight and so forth. And then you see these aluminum droplets. and the smoke coming off from them is the alumina. And the alumina will agglomerate in big droplets, and that goes clunking out through your nozzle. If you watch really close, you can see that it's not just a spherical droplet, but there's like this knob. That's an alumina, they call it an oxide cap. But this has been seen before. I think we did a pretty good job imaging it, but this is nothing new. This is typical. If we replace the aluminum with aluminum lithium alloy, the whole surface changes kind of its characteristics. It's kind of bubbling on the surface. It'll throw off droplets, and then you can clearly see these micro explosions. The droplets just self-disintegrate. So what's going on there? Also, in recent work and stuff we're going to begin looking at is to understand if there's reactions with that lithium at or near the surface. I really think there are based on some data. So this is how we've explained what's going on. If we start off with the initial particle, particles may not be spherical. And in fact, these particles aren't very spherical. As that's heated, it forms a molten droplet. If it's just a single component, say aluminum, that droplet could be consumed, becoming smaller, perhaps. If we have an alloy with a multiple component, the more volatile component, the component that boils at a lower temperature, in this case lithium, will boil off that surface very quickly, and the lithium near the surface doesn't have to diffuse very far, and so it diffuses and goes to gas. And that leaves the aluminum that's not boiling yet. So you have kind of a shell here of aluminum. And under certain conditions, and if you're watching enough of these high-speed videos, you see almost like little volcanoes coming off that droplet. We call that a dispersive boiling type of phenomena. Or you get cases where the entire core of that droplet flashes to gas, and we call that a shattering microexplosion, and we saw evidence of that. So why the different phenomena, and what's going on here? So this graph helps us kind of visualize what's happening. And in short, what you have is as you heat the droplet, the more volatile component, in this case lithium, can become superheated. Stays a liquid, doesn't have anything to nucleate and form a gas, so it gets above its boiling point, but it stays a liquid. There's clear examples. You look on YouTube, you got smooth beakers. You put with pure water into a microwave, and then you throw a spoon in it. It'll flash to gas. That's what superheat is about. And there's a couple of different cases here drawn with the dashed line and the solid line. On the solid line, well, and I should say too. So it's superheated. You keep heating it up. It gets to a point where it says, I can't take this anymore, and it flashes to gas. You exceed the superheat limit. That's this TSH. And so for dispersive boiling, you may have part of that droplet above the boiling point of the volatile component. That's what this line is. And so when that exceeds the superheat limit, this region will flash to gas, but not the whole droplet. And you'll have this dispersive boiling, kind of volcanic type of boiling. And in the other case, with the shattering microexplosion, you could have pretty much the entire core superheated. You exceed that superheat limit, and that whole core flashes to gas and shatters the droplet. A former student of mine started a company, Adronos Energetics. This is Brandon Terry, who's the founder of the company, and he's transitioned this technology to doing rocket motor tests. He developed a coating of the aluminum lithium. When we did our work at Purdue, we used uncoated aluminum lithium. As you might imagine, if you know anything about lithium or sodium, those kinds of metals, they're very, very reactive. In the alloy, it's more protected. The aluminum helps protect it, but moisture and air will still degrade it and slowly react it, so it makes it unsafe to scale to a rocket motor. And so he developed a coating of those alloys and scaled it to rocket motor testing. And this is the baseline aluminized propellant. The same exposure on the camera. So this is a lot brighter. If you look closely, you can see streaks. Those are large droplets, maybe unburned aluminum particles coming out of the nozzle. In contrast, the aluminum lithium, I should have said aluminum lithium. I have a typo there. This is aluminum lithium. First of all, you see that you have the pink color and the plume is a lot less intense. It's a little lower temperature. Plus, the particle size coming out of the nozzle must be much smaller, and you can actually see some structures here. Those are actually shock diamonds that you typically don't see in solid rocket motor plumes. Liquid rocket motors, you see that. So both those things are very interesting. In measured performance, and the performance is actually higher than I would have even hoped for. I'm not sure he's allowed me to tell you the exact performance, but it's looks very good, and he's working with the company to try to actually get these materials scaled and implemented into actual rocket motors. And so embedded wires are sometimes used in solid propellants to increase the effective burning. They increase the heat conduction along those wires. So think of a propellant with some, could be copper, aluminum wires, whatever. And as that heat conduction is improved, it creates these kind of cones, these divots. The inert wires can be problematic though. There's dead weight. They leave slag behind. They have clunky products that go out through your nozzle. Could corrode your nozzle or erode your nozzle. So what about reactive wires or pyrotechnics? This is 50% aluminum, 50% Teflon, and we made this into a foil. This is just burning by itself. We've looked at putting different wires into propellants and comparing them. The copper wire is just a baseline inert wire. There's a nickel aluminum foil that's a commercial product. It's vapor deposited, nanoscale layers of nickel and aluminum. That forms an intermetallic reactive material. And in fact, that material is used for a lot of applications, including welding of big screen TVs and stuff. So it's a commercial product, very fast burning, reactive. Pyrofuse is another intermetallic self-alloying reaction that's used in igniter systems. And then this material, again, it's the mechanically activated, so we've pounded in this case, Teflon inside of aluminum. We made that into a kind of a foil or a wire and put that into a propellant. So how we do the experiment is we have a strand of propellant that we've cast this foil or wire. We put a window here so we can see what the effect of that wire or reactive wire is. And this is a video of 4 different tests. On the left is the baseline copper wire. Yeah, you can see how it forms this V. That increases the surface area and therefore increases the effective burning rate. So higher surface area that regresses back, that means that you'll have more of that propellant burning up at a faster rate. This is the nickel aluminum foil. It's a nanostructured layered material, and it's going much, much faster. You really have a hard time seeing the V structure. It shoots down through the propellant. Pyrofuse is a little bit slower, and our aluminum Teflon foiled material is pretty fast, but maybe a little bit slower than the Pyrofuse. The disadvantage of these materials is they all produce products that are, and in all their cases, are basically non-reactive and form big clunky particles that go out through your nozzle. In this case, the particles disperse into aluminum, and as I mentioned before, propellants often use aluminum anyway, so it'll form small droplets and small particles that are often used in propellants anyway. So this shows you some of the products that come off from these types of experiments. And this is the aluminum Teflon type of material that forms a small dispersive type of thing. So I want to talk about additive manufacturing. And so why do we want to do that in propellants? We can do, so typically propellants are cast, and you have molds, and there's only simple geometries that you can work with. If you could print those geometries, you go much more complex. Likewise, you could think about combining pyrotechnic or reactive wires and so forth inside the propellant, and that could enable other kinds of capabilities and increase the amount of propellant that you could have in a rocket motor. Also, you could fabricate on demand. So you need a certain type of rocket motor, you could print that as is needed. These materials are highly viscous. When you mix up a solid propellant, think of that as like cookie dough. So it's quite viscous, especially if you're trying to maximize the amount of sugar in your cookies, right? And we're trying to maximize the amount of oxidizer in our propellants for performance. Well, that works against being able to deposit that and build up 3D structures. So that's challenging. And the current 3D printing methods restrict the kinds of materials. It's like, oh, we really can't use the binder that we'd like, the polymeric component holding this together because the viscosity is too high. We'd like something that's thermal, softening that will work better, or you will have to restrict the amount of solids that we put in the propellant so that we have a poor performing propellant. So increasing the solid fraction, that increases the surface area that has to be bound together with the binder. The viscosity increases with that, and I think I'll move along. So you would think, well, maybe what we do if we're thinking about printing this viscous material with a nozzle is that maybe we'll just increase the pressure. So if we increase the pressure of a highly solid loaded viscous material, those particles can bind together and the pressure could succeed at extruding just the binder, so it de-wets. And it requires, and that rapidly increases as you go to smaller and smaller nozzles. And you have to have smaller particle sizes for finer nozzles, and this local frictional heating. There's all sorts of problems. So this is kind of the ideal thing. Ideally, we'd like to be able to go to at least 80%, certainly higher. High solids loading for solid propellants are like 88, 90%. We want the printed form to hold their shape. We want little thermal effect because we don't want to heat these materials up because they're propellants, right? They'll ignite. We want to be able to precisely turn it on and off the flow to control dimensional tolerances. We want it to be scalable, low cost. We want low, no porosity in the final parts. If a propellant has porosity, the flame's going to get into those small gaps, pressurize, open up cracks, and then again, it's an explosive. It's no longer a propellant or a rocket. So we developed a new technology recently that satisfies all of those pretty well. We started off with just a cheap printer. This is like a $400 FDM printer. We took all the FDM parts off, added a nozzle. We have a low back pressure. And the secret sauce is a vibration on the nozzle. So people say, well, people have looked at putting piezos and vibrating nozzles. This is nothing new. Well, how you do that exactly is new. And in addition, we use the vibration not only to enable the flow, but we actually turn on and off the flow with the vibration. So we have a low pressure that's not enough to move the viscous material. And then when we apply the vibration, that enables the flow. So you're all engineers. You probably learned this even in high school. Friction is all about a normal force and friction coefficient. So most people, when they look at, this is called direct right, they want really low friction coefficient nozzles. In this case, we really don't care. Because how we're decreasing the friction is actually momentarily decreasing the normal force as that wall vibrates. And that decreases, and then it will slip down. Sort of like a snake swallowing a mouse, I guess. And I'll show you some imaging of that. We've used microscale X-ray imaging. This is an exaggerated image of the vibration. It doesn't vibrate that much. But what we've done is taken a high-speed image and then apply some data analysis to exaggerate it so we can look at the modes of that vibration. And that gives you an idea. And like I said, the regular video doesn't show that much vibration. It's an optical technique. This shows the flow control. We can turn on and off on a dime. And as we change the pressure, we can change the flow velocity, change the vibration, we can change the flow velocity, we can turn things on and off very quickly. This is, you see the scale here, that's a US quarter. This is a little sailing ship printed with Sculpey clay. And when that comes out, there's no UV or anything. That's just a highly viscous clay. It has a yield point. So once it comes out, it stays in that form. The nozzle size is about 500 microns, about a ½ millimeter. There's no viscous printer that could print anything like that. So looking at propellants, this is hand mix. We use a Residine. It's a vibrational type of mixing, get some good structure. We can look at printing parameters like the printing rate and so forth, and we can get a very good strand of propellant printed. This is a micro CT, and the printed is better than just hand cast. Here's some printing. Should have said that the printing with the ship was obviously accelerated. This is regular speed, so it doesn't print that fast on a little ship. But these are very nice, and what I would consider very nice is I can take that propellant up to pressure and it doesn't explode because there's very few voids there. So this is burned at 1 atmosphere. 1 atmosphere is relatively easy to to work well. But at pressure, importantly, it burns well. If we add porosity, though, we can make that strand explode. So we can introduce porosity if we want, or have cases that even at pressure that burn in a normal fashion as you would like. So in this case, we have a fully dense case. So this is burning like a normal propellant. It'll get down to this region, and we've intentionally printed some voids into that sample. And there it goes, almost. Once it gets down there. There. So it shoots down through the propellant and basically explodes that. And we're applying this to a wide range of different types of applications, not just propellants, printing ceramic materials that can be later heated, any kind of high solids loaded material. Another printing approach is fused deposition modeling. And how many of you have used that before? Like MakerBots, those types of things? Okay, a few of you. We use it all the time to make little parts in our lab and little structures or whatever. You can make toys even, and useful parts. But they're typically mostly just plastics, like ABS, and they come on these filaments, and they go into a nozzle that's heated, and you build up a part. Like I said, my world's all about combustion. I like to burn things. So I want a filament that's reactive. So this is ABS, and this is a Purdue symbol. And this is an aluminum PVDF, which is another fluoropolymer. We picked PVDF because we just looked up the melting points of fluoropolymers, and that had the right melting point. So first of all, we have to mix the aluminum with the PVDF, and we have several methods of doing that. And we make little pellets, and then we put those pellets in a filament maker. That's just a commercial filament maker. You can buy those actually to recycle your printed parts if you want, and make new filament to print in your FDM printer. But we use it to make a novel filament. And then we can take that filament, put it into a MakerBot or whatever, and print up reactive parts. This is a little printed puck. It shows that it's reactive. And this is actually just a filament here that you ignite it. It's producing a lot of carbonaceous and also aluminum fluoride products. So as you see here, we could print reactive wires. We're moving towards, as I showed you, reactive wires, if you will, in solid propellants. You can think about printing the solid propellant and the reactive wire together. Hopefully in the next month or two, we'll be doing that. We also have a new project spinning up where we're exploring smart, multifunctional energetic materials with piezoelectric properties. So we're all about novel materials that have all sorts of multifunctionality to them. So you could think about your propellant that is also has embedded elements that could be sensors. It could be activated by external fields to introduce fractures into the propellant to have different functionality, changing the burning rate or detonation even. So we call that piezoenergetics. So it'll be a new area. So we've continually look at a wide range of options to tailor performance, improve the environmental impact, and optimize energetic materials. Showed very quickly a new technology to print very high dense, high solids loaded materials with that are very viscous with no cheating. So if you talk to the vendors of conventional direct write, which is like nozzle printed types of additive manufacturing, they say, well, we had one company say that viscosity is just a number. Okay, well, it's a number that matters, and if you have a certain size, you want to be able, to print as high solids loaded as you can, high viscosity as possible. That approach could be applied to anything with a nozzle. I think we can improve the functionality of that by instantaneously minimizing or decreasing the friction. And then we've showed that we can change the microstructure and affect combustion behavior. And there's a wide range of applications beyond energetic materials. And future directions are to bring different pieces of all this together, piezoenergetics, reactive wires, and so forth. So with that, I'd like to thank you for inviting me to this seminar and spending a little bit of your afternoon here. And I'm happy to take any questions. I think I'm about on time.
10 minutes for questions.
Very good. I'm glad I left time because, yes.
For your 3D printing, what's the layer strength like? Because I know that's a major issue.
Oh yeah, absolutely.
Conventional ones.
Yeah, we're looking at that really, really vigorously now. And I mean, there's a couple, and that's a lot of times there's UV cured binders, and the problem with that is when you cure a layer. If you print things that aren't uncured, then you apply the curing, either heat or whatever, then the layer to layer will intertwine, and that layer to layer adhesion may be pretty good. But if you have a UV cured binder, then you kind of close off those molecules for binding to the next layer, and that could be a huge problem. For the FDM, my colleagues actually published a paper recently on not even energetic, but just FDM, and came up with all sorts of mechanical testing of quantifying. Okay, if you print different orientations, how does it affect the strength? So that's a real key issue that we need to look at. But there are ways. I was just this week talking to a colleague that say you have a UV cured. So for UV cure, you put the polymer down, and then you apply UV light, and that cross-links the polymer, and it makes that interface, which could be very problematic. There are ways you can bring in. I think he was saying you take an ionized gas and open up those links. So what I think going forward might be good to make sure you minimize those problems is to do that to improve the layer-to-layer adhesion. We haven't seen like direct problems. Okay, that's a huge issue because most of what we've done, we haven't completely cured at every layer. So we have the final material and then cure the whole material at once, and I think that's going to be minimal. And the FDM looks pretty good. It's melted, and the next layer kind of melts and bonds pretty good. But that's a really good question and something that we're very well focused on. And it may depend on the kind of polymers too. So there may be some polymers that, if you will, adhere to themselves well, right? And they chemically bond to layer. But I think that's a really good point and something that we're starting to think about a lot. Yes.
When you're ball milling the aluminum into PTFE, how are you avoiding premature oxidation of aluminum particles?
Yeah, you really need to, especially for that system because you have the Teflon and aluminum, and yeah, guess what? Those are reactive. First of all, for that system especially, and for really all the ball milling we do it remotely, because we actually, we use a specs mill in that case, so it's a plastic container with the ball mills. We have different ball mills for different applications. For that, we have kind of a plastic container with the ball mills in there. We put an inert gas. That'll help to some extent, but it doesn't need any oxidizer. And we actually take it to reaction. So we see where the cliff is. We blow it up. Okay, and it's violent. It's like, okay, we want to stay away from that. We back off from that and carefully look at, we back off a lot from that. We know where our limit is on the time of milling and so forth. And then we back off from that a lot, and then we look at how much of that material is reacted as we change the milling time or milling parameters. We use a DSC TGA, differential scanning calorimeter and thermogravimetric analysis, to see, okay, what are we doing in terms of the onset of exothermicity, and are we cutting into the energy by this premature oxidation? So you have to watch that very carefully, and it's a safety issue as well. Excellent question. Great questions. Anybody have even a question that's not as great as those two? Be fine. Yeah.
I have a quick question.
Yeah.
With regards to the introduction of the microstructures to change the combustion behavior,
Mm-hmm.
did you find that, was there any optimal equation between the space allowed between the layers, or anything related to what particles you're using?
The general question, the answer is yeah. I mean, it makes a big difference. Like, and I'll give an example of, so like the nanofoils. I mean, that's not material that we make. As those are deposited, as you go thinner and thinner, the inner layer space, right? You make thinner foil materials. The propagation speed will go faster and faster. But you get to a point where even you deposit the layers, there's a little bit of partial reaction that occurs, and it'll start to slow down. And you'll have partially reacted material. So there's often, in general, an optimization of the layer thickness and so forth. For nano-aluminum particles, aluminum will form a passivation layer, an oxide coating, right? So if you scratch aluminum, it will oxidize quickly and form maybe a 4 to 6 nanometer thick passivation layer. For particles, you have the same thing. So micron aluminum, that 4 to 6 nanometer thickness for 30 micron particle, do the math, it's like 1%. Don't worry about that. But for a nanoparticle, and by nano, I'm thinking like under 100 nanometers, you get down to 50 nanometers, and all of a sudden half your aluminum's already oxidized. So you're bringing to the game, you threw away half of your fuel, which is, and so you have to compromise there. So I'd like smaller particles to increase the kinetics, have more surface area, shorter diffusional distances, but I don't want to go so small that I'm losing energy. Or you could look at strategies of, some sort of, coatings on the aluminum so you avoid the passivation. And there's a couple companies actually that make nano aluminum particles that in situ into a binder system that have these coatings on it that avoid the oxide altogether. And we're actually looking at some of those materials and putting those into propellants, and also doing our ball milling with that polymer material and introducing those inside the aluminum particle. So we do the bottom up, the in situ formed nano aluminum particles, and the top down milling process to form micron-sized particles with nanoscale inclusions. Yeah. So that's an excellent question too. And that you're always juggling that, and again with safety too, right? Nanoscale thermites, for example, can just be really, really, as John well knows, I'm sure, electrostatic discharge sensitive, and friction and impact. Micron-sized powders of thermites are really difficult to ignite, very insensitive. So you may pick a size where you have the right balance. Less sensitive, or adequately insensitive, and a higher regression rate or burning rates or reactivity that you're after. And there's other ways to control that as well. So if you have really fine particulate, you may bring in a binder or other material that will desensitize it adequately, and so forth. All right.
Steve, thank you so much for giving a very easy to understand introduction to the very complicated research.
I'm pretty simple.
So you mentioned there is a company which can produce like energetics. So your student has a company.
Yeah.
Do they sell product?
Do they sell the product?
Right.
They're working towards that. So they've got they're at an interesting point right now. So he's been working with this company. He started the company 2 or 3 years ago, and their first objective was to deal with the issue of the coating. We knew that we could have tested the rocket motors at Purdue, but it's like that's not safe because we knew it oxidized slowly. That's going to heat up. I don't want small strands. Oh, that's okay. We can if it inadvertently ignited, we could deal with that, but not in a motor. So he solved that problem and did these. There were 4-inch diameter rocket motor tests. And that looked really, really good. And so now, the question is going forward. What happens? There's one possibility that a large company could say, okay, we're just going to license the technology or buy the company. That's one possibility. Another possibility, and he's working towards this as well, of being able to, make the powders and then sell that. And so and to scale that. And so he's actually got in partners to scale the coating method that he developed, and he has a patent on the coating method, and also the quantities. And a good question would be, well, can you get good quantities of aluminum lithium? And I mean, you can get small quantities. You can just look it up. You can buy the aluminum lithium that we did, but it's very expensive because nobody makes large quantities of it because there's no application. But the question is, could you get large quantities? And it's really the same question you have for lithium-based batteries. And the answer seems to be, yeah, there are resources for lithium that you can get, and then form the alloy. The aluminum lithium. So we started off with Sigma Aldrich, just order it online. We get a small amount, we pay a lot, and we started with that, and that was fine for tiny samples. Then we decided we wanted kilograms of this. How do we get that? And the only source that we could find was actually China. And so we bought several kilograms for China, it's a long story I'll tell you over dinner about buying aluminum lithium from China. It was crazy. But he's my former student has identified partners to make the aluminum lithium in bulk, and also to scale up the coating. So I think he's solved the 2 big problems. So if you're thinking about being an entrepreneur, you got to identify what the real problems are and figure out how you're going to solve that. One was it's not totally stable, and I think he's done that. And then he's still working on the scaling.
Right. So I have a group of students here. They are looking for some solid field. So for their first year project.
Mm-hmm.
So they want to buy some like a solid field, like a packet or
A propellant, or
right.
Yeah.
I don't know what you can buy in Canada, but in the U.S. you can certainly buy the ingredients for solid propellants. I would caution you to be very, very careful. make sure you get people involved that are very experienced. There's high-powered rocketry clubs, at least in the U.S., that a lot of my students have become involved with, and they have certifications on safety and those kinds of things. In the U.S., there's a company like Firefox that you can buy propellant ingredients. I do know there's I don't know if they sell for like hobbyists, but there's certainly companies. I thought there was one in Toronto that sells rocket motors for hobbyists. I'm not sure. I know there's a company, Cicerone, I think, in Toronto. I don't know what they sell though.
Maybe I can talk to you guys after, but in Canada, making solid fuels is a little bit more restrictive than.
Yeah, I imagine it would be. Yeah. So you got to become U.S. citizens and then come down. But.
Have you looked at using the reactive wires as like a secondary strengthening agent, say in the rubber matrix. So I know in concrete you can use metal wires to as part of the aggregate and as a instead of rebar. Have you looked at doing this and seeing what the properties it would be if they're more randomly distributed rather than sort of?
That's an excellent question. Yeah, I think the answer is no, we haven't done that, but it's certainly something that, like I said before, the layered adhesion and more generally the mechanical properties of the printed structure need to be looked at. And what you're saying is well taken. And people have put inert wires in propellants and then randomly oriented, so like sort of like staples, like the middle chunks of stuff, and that certainly would affect the mechanical properties as well. So like in general, you have to quantify the mechanical behavior and the combustion behavior and the whole thing. Because, you know, every material almost is multifunctional, and so you got to make sure you cover both that. That's an excellent point as well. All right, I think that was the last question.
That's what I said. Does somebody have a really quick question? Or if not, perhaps we can discuss with Dr. Sun after. But please join me in thanking him for a very exciting
Thank you.